SwayamPrabha. Digital India. Educated India.
So, this is to give you some glimpse of the different methods of simulating particle laden flow. I have included few examples. So, this is the DNS of particles in decaying isotropic turbulence by Ferrand and Elgobashi. So, decaying isotropic turbulence means the turbulence which decays with time. Okay. So, in numerical simulations, simulations of say homogeneous isotropic turbulence, to sustain turbulence itself, an extra term is added in the Navier-Stokes equation, that is the forcing term. It is called a forcing term. This is not with particles, even without particles the turbulence has to sustain. See, in experiments we use, let us say we use fans to generate, or multiple fans which are in opposite directions to generate homogeneous isotropic turbulence. But in numerical simulation you do not have that. So, an extra forcing term is added to the Navier-Stokes equation without particles to sustain turbulence. But in case of decaying isotropic turbulence, that term is absent, such that the turbulence would decay naturally because there is no production mechanism. But some people consider this as the ideal way to study turbulence. So, anyway, so in this case they have simulated how particles behave in this decaying isotropic turbulence, and this is an example. We will again revisit this to discuss what exactly we see here. This is an example of large eddy simulation of polydispersed particles in coaxial turbulent jets. So, in this case we have a turbulent jet at the center, and around this there is a co-flow of turbulent air also. So, you can say there are two jets, one central, one annular, and particles are added to the central jet. So, here the idea is to understand the dispersion of particles in this kind of configuration, which is a very relevant configuration to practical injectors which are used in industries. So, you can see here how the dispersion of particles is affected as we change the co-flow velocity ratio. So, in this case there is no co-flow, only the central jet carrying the particles. Here there is some co-flow and the co-flow velocity is increased in this case. So, basically we see that the co-flow has a strong influence on the particle dispersion. This one is an example of RAN simulation for pulsatile spray injection. So, this kind of pulsatile spray refers to the spray which occurs for finite period of time, for example in IC engines. So, in this case the simulation is performed for a gasoline direct injection system, GDI injector. So, the spray is injected under high pressure condition, and this injection occurs for a very short duration of time. So, it is an unsteady spray, you can say. So, here the simulation is performed for different ambient temperature as well as ambient pressure. So, here you can see what happens to the structure of the spray as the pressure increased, let us say from 1.4 bar to 5.8 bar. So, you see that it significantly it is modified. And also here through this simulation we can calculate the velocity of the droplets, and at the same time we see the velocity vectors for the surrounding airflow. So, basically this is a two-way coupled simulation using RANs. So, that is why you see the presence of the air velocity, even if the initial air velocity was 0 or the spray was injected into a stagnant ambient condition. But because the particles and the surrounding flow are two-way coupled, which is always the case in case of a spray. Because of the motion of the particles, the gas flow sets in this case. Basically, you can see the spray structure, how it changes for different operating conditions. However, the accuracy issues persist here, but it depends on what do you want to investigate. For example, if you want to qualitatively assess, okay, what happens if the ambient pressure is high? What will happen to the structure of the spray? Yes, so here you see this, and that agrees well with experiments. Also, if we, though not shown here, if we calculate the penetration length of the spray. So, penetration length means from the injector exit to the tip of the spray, how it changes with time as the spray, as the spray injection continues to happen over time. So, that agrees well with experiments. However, if you want to match, for example, the droplet size or say the local droplet dispersion, that is difficult. Okay. The details you may not be able to capture accurately. Some dispersion of droplets here you see are present mainly because of the random walk model that was implemented here. That gives some effect due to the turbulence. Okay. But one-to-one comparison or very close comparison with experiments is not possible here. Okay. Okay. So, then we will move on to understand some of the mechanisms of particle turbulence interaction. So, what are the mechanisms, what are different ways in which this interaction takes place? So, there are broadly you can say two different ways to look at this. First one is how turbulence affect the particles, okay, in particle laden flows. Now, there are multiple effects here that you can see. For example, preferential concentration or particle clustering, crossing trajectory effect, turbophoresis, gravitational settling modification, enhancement of particle collisions. So, all these effects are due to how turbulence influences the particle behavior. On the other hand, we have the feedback from the particles. The particles can also influence turbulence, and that is what we were discussing, if you remember the modeling part. So, how do we handle this, the modification in turbulence due to particles? So, this is mainly due to the momentum coupling or the drag feedback. However, there are other effects also, that is wake generation, coherent structure disruption. The particles would try to disrupt the eddies or the coherent structures. Similarly, in case of bubbles, we can have buoyancy driven turbulence. In general, if the dispersed phase density is less than the density of the carrier phase. And we can also have collision induced fluctuation. Because of collisions, there is now modification of turbulence. So, particles themselves locally they will modify the turbulence, either they can enhance or consume or dissipate more turbulence, but collisions can also lead to modification in the turbulence. Okay. So, we will go through some of these aspects in some detail. It is not possible to cover everything, but some important aspects I will discuss. The first one is preferential concentration effect. So, what is meant by preferential concentration effect? So, when we add particles to a flow, let us say you have homogeneous isotropic turbulent flow, that is, there is no directional preference in the flow as far as statistics are concerned. So, what do you expect? You have a turbulent flow, let us say in this room you create turbulence some way and you add some particles. You expect the particles to be randomly distributed because the turbulence itself is random. Okay. So, when the particles are randomly distributed, what would you expect as far as the local concentration is concerned? You expect the concentration to be uniform everywhere because they are all randomly distributed. Okay. So, you expect something like this. You have a flow in which particles are added. But in reality, what you may get is this. That is, particle distribution is non-random. That is, somewhere the particles have accumulated and somewhere there is a region of depletion. There are no particles like this here. Okay. And you see this throughout the domain. Now, the question is why this happens? What causes this? So, in a turbulent flow, small inertial particles do not remain uniformly distributed as we have seen here. Instead, they tend to accumulate in certain region of the flow, forming particle clusters, leaving other regions depleted. Now, this is called preferential concentration or turbulent clustering of particles, which is one of the most important and fascinating particle turbulence interaction phenomena, and it has attracted researchers since last 2 to 3 decades. Okay. So, what is interesting about this is a dynamic phenomena. What is meant by that? So, it is not like you will see particle clusters like see here or the same topology of the particle distribution at all time. So, this is one instantaneous feature. If you take, let us say, photograph at another time instant, you will not be able to see exactly the same pattern. Okay. You will see another pattern. So, this means that the clustering or preferential concentration phenomena is dynamic. Put it in other words, let us say I go to this region here and I calculate the volume fraction. You know what is volume fraction of particles. What is that? Volume of particles per unit volume. Or you calculate, let us say, the bulk density or mass loading ratio, any parameter you calculate. That parameter would vary spatially, it will vary temporally. So, at the same location, if now at the same location I calculate the volume fraction and plot with respect to time, I will see something like this. At the same time, if I plot with respect to space, also I will see something like this. So, this means now we have spatial temporal fluctuation of particle concentration. Okay. So, this is a main consequence of the preferential concentration effect. Now, why that is important? Because it can cause local flow modification. Locally the flow is modified because of accumulation of particles or depletion of particles. Now, it can modify the drag, heat and mass transfer from particles. Okay. Enhanced concentration influences local exchange rates. So, for example, if particles are coming together at some place, then the drag on individual particles will be modified. The question is, can you still use Stokes' drag? Can we introduce some correction factor? Yes, people have introduced some correction factor, but not for phenomena like this, an unsteady phenomena. What is that? That is, if you track, let's say, one individual particle, the number of particles around that is not constant. One particle which is within, let's say, one cluster, we will see the definition of cluster, formal definition of cluster later, but one particle within a cluster, okay, it need not stay in the same cluster all the time, because the particles accumulate and then they segregate also with time. So, it is not like this is static, this is dynamic, and that is the reason why the momentum, mass and heat transfer from the particles become also dynamic. It changes with time. Okay. Now, this may lead to enhancement of collision rate, but this is still an ongoing research. Yes, people have identified that preferential accumulation phenomena leads to increase in particle collision, but what is the mechanism? Is it because locally the loading increases to a very high value or not? That is still under research, you can say. But yes, if collision happens, that influences the, for example, particle size distribution if the particles are liquid droplets. Okay, and this phenomena is important in clouds and sprays. So, now the question is, why we have preferential concentration effect? First of all, to understand this, we need to look at how do particles respond to turbulence. So, for that we have defined the Stokes number, which is the ratio of particle response time to time scale of turbulence. So, if the Stokes number is much smaller than 1, then the particles act as a flow tracers. We have discussed this earlier also. So, when I say Stokes number less than 1, this is with respect to which turbulent ED now? Okay. Let us say with respect to all turbulent EDs, or I can say Stokes number based on Kolmogorov scale itself is much less than 1. So, this means that it will be obviously much even smaller for large scale EDs. Why? Because for the same particle size, the turbulent time scale increases as we move from small scale to large scale EDs. Okay. So, in this case, the particles can closely follow the ED. Okay. So, in this case, we can expect the particles to be randomly but homogeneously distributed. So, no preferential effect. If the Stokes number is much larger than 1, so here I consider Stokes number based on, let us say, large scale EDs. So, if it is Stokes number is larger than large scale, greater than 1 for large scale EDs, then obviously it will be even more greater for smaller EDs. So, in this case, there is no response of the particle due to the turbulent flow fluctuations. It just moves like a ballistic particle. Okay. But when Stokes number is of the order of 1, now some interesting phenomena occurs. And what happens is that in that case, the particles, because of their finite inertia, they are unable to follow the fluid streamlines closely. So, in this case, we know that the particles will follow the streamlines always. In this case, they won't. But in this case, they can follow, they can't follow the fluid streamlines closely, but at the same time, they cannot behave like a ballistic particle as well. They cannot just move out of the flow. So, they respond to the flow in a certain way. So, what happens as shown here, the particles are basically centrifuged out of the EDs due to their inertia. So, basically they try to come out of a region with high vorticity. They tend to move towards a region where the vorticity is low. Okay. So, they preferentially accumulate in strain dominated regions, that is regions between EDs. So, this is the region. Okay. So, where they try to accumulate, and this effect becomes prominent when Stokes number is of the order of 1. Okay. So, basically preferential concentration effect happens when the particle relaxation time and turbulent flow time scale are of similar order. That is why Stokes number is of the order of 1. Now, I will show you some examples from the literature. So, people have done studies in various flow configurations and they have found this effect. So, for instance, in this case, these authors did experiments in a particle laden channel flow. So, it is a vertical channel in which they have airflow and you add particles. Which particle they use? Different solid particles, for example, glass or other particles, so that they can realize different density and size. Why? Because the particle relaxation time has these terms. So, particle relaxation time depends on density and size. So, they varied density and size. So, they used different particles also and they conducted this study. So, on left side you see how particles are distributed when Stokes number is very large, like 40 or so. But when Stokes number based on Kolmogorov scale is of the order of 2, is similar to 2, then you see how the particles behave now. So, this is an experimental study where you can clearly see the preferential accumulation effect taking place here. Okay. Now, similar observations people have noticed in numerical simulations, mainly in direct numerical simulation of particles. So, why direct numerical simulation? Why not RANS? Can we see this effect in RANS based modeling? The answer is no. Why? Because this is a dynamic phenomena. While in RANS model, you solve the time average equation only. So, if I take multiple photographs, let us say here at different time instants, and I collect these photographs for a very long time scale. So, what is the definition of a very long time scale? The time over which I will take the photograph is much larger than the largest or the large ED time scale or ED turnover time. Let us say if the ED turnover time is 1 millisecond, I will take these photographs, let us say for 1000 seconds. Okay. So, and then if I average everything, I won't be able to see this instantaneous phenomena. Why? Because the particle concentration will get averaged out. Okay. So, this is the reason why you cannot capture this in RANS based modeling and up to some extent in LES modeling, because there we resolve large EDs, but we consider small EDs also, although we are using a model for small EDs without resolving them. So, here you see in the DNS simulation. So, now the DNS simulation allows a very systematic investigation here. So, you can, for example, you can change Stokes number in whichever way you want, which might be difficult to maintain that in the experiment. So, this is the case of Stokes number of 0.05. So, you see this homogeneously distributed. Now 1, you get this some preferential effect, concentration effect, then 5, then even 10. Now, here lies the interesting thing. So, the question is, why do you see the preferential accumulation if it is more than 1, either in simulation or in experiment? So, the thing is, we should not take this value literally. So, this should be of the order of 1, but still it is interesting what causes this clustering behavior or preferential accumulation behavior when we have Stokes number 10. Okay. Also, you see that for different Stokes number, even if these are all order of 1, the behavior of particle clusters or qualitatively the length scale of the particle clusters are not same, it changes. So, this means that the clustering behavior changes with Stokes number. It is not like for all Stokes number, even if it is of the order of 1, the behavior will be same. No. Yes, we can say that for all cases we see preferential accumulation effect. Then this is an experiment. So, people have tried different configurations also. So, this is an experiment in which the authors see this, they have done this nearly 30 years ago, more than 30 years ago. So, here they considered one jet of air, but they used speakers to perturb or force the jet. So, here you have a jet under periodic forcing. So, they forced the jet such that there is some pulsation in the jet, and they wanted to study how the particles behave. So, this photograph what you see here is the example of the case where they are not forcing the jet. So, this is just one turbulent jet. You can see the Reynolds number is quite high and they introduce the particles, and the particles mostly they stay at the center. So, do you identify any particle dispersion? Do the particles have some radial dispersion? Mostly no, they mostly move axially. But now they perturb the jet. So, they have a forced jet here without particles. Now, in this case they show only particles, but without the gas flow. So, here they show the air flow, but here they show air flow, the particles without the air flow, but both correspond to the same experiment. So, here now you see some radial dispersion of the jets. Okay. So, why this happens? Because in this case the flow time scale has now changed, and now the particles are responding to the flow, while in this case they are not. Now, this is an example from another experiment where they created homogeneous isotropic turbulence. So, this is experiment. What we have seen here, this is isotropic turbulence, but DNS simulation. So, in this case also you see how preferential accumulation effect segregates particles and how we see voids, these are called voids, and the clusters when the Stokes number is of the order of 1. Now, this is, I had shown this photograph earlier today. So, as I said, in this case they considered DNS of particles in decaying isotropic turbulence, and here you see the preferential segregation of particles. So, what they have done is they have superposed the particle position on vorticity contours. Okay. So, you see that wherever you have finite vorticity, you do not have particles there because of centrifuging of the particles, and they accumulate in the region between vortices. But this is also, you should not consider it literally. It is not like there are certain EDs that we can visually see. Okay, the vorticity contour depicts it up to some extent. Okay. But mostly you see that the particles are not present wherever you have strong vorticity. And they have also studied the effect of gravity. So, in this case they considered particles which are fairly smaller than 1. So, we should not expect any preferential accumulation. As you can see here, the particles are present even when we have strong vortices. But this was done without gravity. Now they introduced gravity in their simulation, and you see things have changed. So, this is also interesting. So, what they have observed is that the particles tend to accumulate on the side of the vortical structure whose instantaneous velocity has the same direction as the gravitational acceleration. So, if you have a vorticity, an ED like this, then let us say this side corresponds to gravity, then particles accumulate more on this side compared to this side, okay, which is an interesting phenomena. So, the point here is that it is difficult to generalize any conclusions, and when we generalize we have to mention the conditions also. In the previous DNS simulations they did not consider gravity. Now you see gravity, with gravity, even with low Stokes number particles we see some preferential sweeping of the particles. So, now the question is, what are particle clusters then? So, particle clusters are the group of particles that remain close to one another on time scales long compared to some turbulent time scale. So, one can argue that, okay, what if preferential accumulation of particles happens? So, the particles come together for some time and then they again disperse out. So, why should this matter to us? Because they are again dispersing out of the zone where they had accumulated. So, why this is a concern? Now, this is a concern when the particles come together and stay for some time scale which is comparable to the turbulent time scale, or in other words the large ED time scale. So, if they are dispersing out before that, then it will not have much effect. So, we call those group of particles as clusters whose lifetime is comparable to turbulent EDs. And now this only dictates the length scale of the clusters. So, the length scale of the cluster is mainly linked to turbulent ED scales that most strongly interact with the particles. So, the question is, what sets the cluster scale? So, here you see here the clusters have some scale, you see they have some scales. Okay. Now, what factors govern the length scale of the clusters? That is the question. So, this is basically mainly linked to that turbulent ED which mostly interact with the particles. Now, when we can expect one ED to interact with the particle? If the particle relaxation time is comparable to the time scale of that ED. So, then we can say that yes, they will interact with each other. So, with this argument we can say that maximum clustering would occur when this condition is met. Okay. So, or when Stokes number is 1. And if we have particles with size particle size itself is comparable to Kolmogorov scale, then we can say that the length scale of the clusters also would scale with the Kolmogorov scale. So, people have actually calculated or measured in numerical simulations and experiments respectively the length scale of the clusters, and they found that the average length scale of the clusters always is of the order of the Kolmogorov scale, let us say 10 times Kolmogorov scale, even larger than that, 20 times, 30 times Kolmogorov scale, but you can compare that with the Kolmogorov scale, that is what they have found. But then an interesting question arises, what happens if we have now polydispersed particles, that is particles with different size, what will happen to clustering? Will clustering happen, and if it happens, what will be the length scale of the cluster? So, that remains a even now that remains a interesting question and an open question.